Lecture 7b of differential equations in linear algebra is about matrices and linear transformations. It goes with section 1.5 of my online textbook, Visual Linear Algebra Online, at my blog, infinityisreallybig.com. Quite a mouthful. I will warn you, though, that the content of the blog is going to be a little different feel than what I get across in this lecture. I think what I get across in the lecture will be the best way to do it for a lecture. In the blog, I try to build up the definitions. Here, I'm just going to pretty much tell you the answers. Whereas, again, in the blog, I'm trying to help you understand the motivation for things. So matrices and linear transformations, and we're going to especially visualize them in low dimensions. We're going to be ahead of the blog and think about higher dimensions at the same time. In the blog, I also stay in the low dimensions, but now in this lecture, we're going to look at higher dimensions as well. So what is a matrix? Given two positive integers, whole numbers, 1, 2, 3, 4, 5, 6, etc., call them M and N. An M by N matrix, real matrix, the entries are going to be real numbers, is just a rectangular array, or a table, essentially, of numbers. You got some rows, you got some columns. In fact, you have M rows, and you have N columns. Keep that distinct. M, the first number, is the number of rows. Maybe M is 10, you got 10 rows. And N, the second number, is the number of columns. Maybe N is 37, you got 37 columns. We typically put parentheses or square brackets around the entire array, around the entire matrix, and we think of the entire object as being our matrix. I will use both notations. That'll be a little bit confusing. I'll typically use the parentheses notation for smaller matrices, and especially when we're talking about differential equations, because that's what our textbook for differential equations does. And I might use the square brackets more for bigger matrices, because I just think it looks better. But either notation can be used. The important thing is that it's an array. In this case, we're looking at a 2 by 4 matrix, 2 rows and 4 columns. The 1, 1 entry, first row, first column is 5. You might call this A11. That's supposed to be an A there. The 1, 2 entry, first row, second column, is -7. You might call that A12. The A13, 1, 3 entry is pi, A14 is 0, A21 is the number E, second row, first column, A22 is 1/2, A23 is -42, and A24 is 9. That's the notation we sometimes use for the entries. But again, it's the entire thing that represents the matrix, and we often give the matrix one letter for a name. It's usually a capital letter, like capital A is the shorthand name for the whole thing. And these are equal. These are the same matrix, it's just different notation. Okay, so there's an example. Two matrices are said to be equal, the same matrix, if and only if they have the same dimensions, 2 by 4 in this case, and each of their corresponding entries are equal. Okay, so you've got two 14 by 23 matrices. They're going to be equal if and only if, column A and B, A11 equals B11, A12 equals B12, A13 equals B13, etc. They have to have the same numbers in the same positions, and they have to have the same dimensions or size, same number of rows and same number of columns. Column vectors are matrices. We've talked about vectors before, and column vectors written as columns. We often think of a vector V in our M-dimensional space, where M is some arbitrary positive integer. Could even be a million or a Google or whatever. It could be humongous, as an M by 1 matrix. So if M is 3, for example, we could write V as, say, the vector 1, 2, 3. Those are the components. That would be a vector in R3, three-dimensional space. It's got 3 components. It is a 3 by 1 matrix. In general, it's an M by 1 matrix. Talking about vectors here, we're thinking about them purely symbolically with numbers, not necessarily thinking about arrows, not necessarily thinking about I hat and J hat, if you know what those are. We will come back to those later. Just thinking about them essentially as matrices. Numbers are matrices. Wait, they are? Yeah, if you want to think of them that way, you could think of any number as a 1 by 1 matrix. If we want to. We got also thinking of those one-dimensional vectors. You ever think about that? Essentially, think about a number line. A number on a number line could be thought of as a point. That's the way it's usually done, but could be thought of as a vector. An arrow that's either rightward pointing or leftward pointing. Maybe this arrow represents the number 5 because it points to the right and is 5 units long. And maybe this one represents the number -2 because it points to the left and is 2 units long. Numbers can be vectors, and we could write this. And we could put parentheses or square brackets around if we wanted to. Or we don't usually do that, of course, but we could, and in fact in this lecture I will do that sometimes to make a conceptual point. An important conceptual point, lots of subtle details. Conceptual points that are often confusing for people. So you need to help yourself get past things that could be confusing. Topic of lecture 6B was linear transformations in 2 dimensions. Very geometric topic. We talked about rotations and reflections and dilations and projections. Pretty cool. This particular lecture is more algebraic, arithmetic. We're doing symbols, symbol pushing, algebra, that kind of thing. But it's still the same kind of topic. It's still related. We will do some graphical things in a bit. Hang on for those. Those will be helpful. But we need to do some more abstract stuff. We define linear transformations from R2 to R2, 2-dimensional space to itself, as a certain kind of function. You might have wondered, how can we do linear dimensional space in the last slide? You can think about it mathematically, even if you can't visualize it. Now, the following type of formula. I have purposely written this in many ways. That's purposeful. At the outset, I thought of it in terms of this thing equaling this thing, although initially in lecture 6B, I did it as a system of equations. But now I'm saying this equals this as a 2-dimensional vector, a 2x1 matrix in both cases. This is a function. When I write t of x, or t of this column vector xy, I'm emphasizing it's a function, t of an input. And the u over here represents the output. Don't be bothered by these different notations. It really means the same thing. It's just different ways of representing the same thing. This boldface x here represents this entire column vector xy. Don't be bothered that it's an x there and an x there. This one's boldface, that one's not. They are different symbols. This boldface u represents this entire column vector uv. Linear equations in x and y here. ax plus by, cx plus dy. For some constants, in this case real numbers a, b, c, and d. By the way, complex numbers and imaginary numbers are useful in differential equations and linear algebra. We're just not talking about them now, for the most part. Okay, well, you might say, well, can I add a constant in these things? Wouldn't they still be linear equations? You could. You could define linear functions that way, but it turns out to be more convenient to do it this way, for reasons that will become more apparent as we go on. And this is the key thing that makes these things satisfy. Any such functions automatically operation preserving, you can't add constants in here that are non-zero and keep these properties to hold still. T of x plus y is t of x plus t of y for all vectors x and y in R2, 2-dimensional space. Think of them as column vectors, 2x1 matrices if you want. And t of lambda times x, where lambda is a scalar, is lambda times t of x. In effect, the t can be distributed, is a way to think about it, but it's not really the distributive property in the usual sense. Okay, I'm not multiplying t times these things. T is a function. This is t of x plus y. This is t of x, this is t of y. This is really key, actually. Okay, this is more important than you might imagine. More succinctly, we could also write this. T of an arbitrary, this has got a name here, this is called a linear combination. Linear combo. That says LIN, kind of hard to see, combo. Linear combination. T of a linear combination where you are combining two vectors with scalar multiples as well, by addition. is the corresponding linear combination of the outputs of t of x and t of y, where you've got the same scalars alpha and beta, and you're still adding here. Okay, the idea of a linear combination is pretty important. Okay, so this is true. And in fact, we could also write this with summation notation for an arbitrary number of terms. T of this summation, lambda I times xi, is the corresponding summation of the lambda i's times the t of xi's. Summation notation makes some people feel uncomfortable. We could, of course, write it out without the summation signs there. We could write t of lambda 1 x1, I use half arrows for my vectors here, plus lambda 2 x2, plus dot dot dot, plus lambda n xn. That's what that summation sign means there, equals lambda 1 t of x1 plus lambda 2 t of x2 plus etc. plus lambda n t of xn. That's how you'd write this same property without the summation symbols there. Okay? That can come in handy. It will come in handy for us. These are very important. Look at this formula again. I don't know about you, but I'm tempted to look at the constants, the A, the B, the C, and the D, and say, hey, they form a rectangular array of numbers, a matrix. Don't they? Well, of course, there's this other stuff in there. There's the x's and the y's and the plus signs. But if I just ignore everything else and just focus on the A, B, C, and D, they form a matrix. It's not good enough motivation to show you what I'm about to show you, but it's going to be our motivation, our justification for this particular lecture. Again, in my blog, it's more systematic. Maybe we should think of the output vector, this thing, as being a product of that matrix, A, B, C, D, that 2 by 2 matrix, call it capital A, times the vector x, whose components are little x and little y. The vector boldface x, whose components are non-boldfaced x and y. In other words, add that to the notation. Same notations here, but I've added something here. I've taken these coefficients, these A, B, C, and D, and put them in a 2 by 2 matrix without the x and y. And then I drew x and y as a 2 by 1 vector there, a two-dimensional vector. And I'm essentially pretending that's a multiplication. Is this a good idea? Yes, it turns out to be a very good idea. This is so essential. So many things that are so subtle that just, like, why would that be important? They are essential. Thinking of this is my matrix capital A, and this is my vector boldface x, or x with an arrow above it there, and I'm thinking of that as a multiplication. Ax is a multiplication. T of x is not a multiplication. That's t applied to x. Function notation. Input for the function. Output of the function is over there. But I'm saying t of x is A times x. This is a formula for this function in terms of this matrix capital A. Okay. Here's another way to look at it. We can think of the product AX as, oh, there's that word again, the term linear combination of the columns of A with the entries of the vector x, that column vector, as the coefficients. I'm also going to call those weights. Like the alpha and beta were coefficients. In the summation, the lambda 1, the lambda 2, the lambda 3 through lambda n were coefficients or weights. And the x1 through xn were vectors. So now I'm doing one new thing here, is that I'm writing this thing here. And that thing does jive, if you want to use that word, with scalar multiplication of vectors and vector addition, because if you do this thing, if you think of the scalar multiplication component by component, multiply x times each component here and get x times a and x times b, which you can write as ax and bx. And y times c and y times d, which you can write as cy and dy. And then you add the vectors component-wise. You get ax plus cy and bx plus dy. Okay, basic kinds of observations that have incredible importance for generalizing in this case. Not quite to the generalization yet. Notationally, we can let boldface A1 and boldface A2 represent the column vectors of the matrix capital A. In other words, here's capital A right here. This thing could be the vector A1, and this thing could be the vector A2, though if I wrote it out by hand, you'd have to put parentheses around those. And we could write the linear combination like this. This is the new thing right here. I've purposely made these humongous long lines here of equalities to emphasize different things. They're all important ways of thinking about it. Let me go through it again. Boldface U is the vector whose components are U and V. A two-dimensional vector, which I can think of as a 2x1 matrix. That equals T of x. T is a function. U is the output, x is the input. Boldface X is the two-dimensional vector whose components are little x, little y, non-boldface. The formula for that is this. Ax plus by equals, and cx plus dy are the components of the output. I can think of that as a matrix, capital A times the vector x, which I can write like that. That can be thought of as a linear combination of the columns of capital A. And if I use shorthand notation for these vectors, I can also write that. These are all super important things if you're really going to get this stuff. This turns out to be the key way to think about linear transformations in general, along with matrix multiplication, from any dimensional space to any other dimensional space. It doesn't have to be 2 dimensions to 2 dimensions. It could be 17 dimensions to 5,000 dimensions, okay? It doesn't matter. This way is the way to think about how to define the linear transformation via a matrix multiplication. So let's get into those details. Let A be an m by n matrix. Again, m and n could be humongous. Or they could be not so humongous. Let X be an n-dimensional column vector. In other words, an n by 1 matrix. We define the product AX. Most important thing is that it's a product. You could call it a matrix vector product. You could call it a matrix product because both of them are matrices. To be the linear combination obtained by taking the columns of A and combining them with the entries of X, the numbers in the column X, column X1, X2 through Xn, say, as the weights, the coefficients in front of those column vectors. In other words, if A is written in this way, just shorthand notation here, A1 is the first column of capital A, A2 is the second column of capital A, through AN is the nth column of capital A, where each of these A's is m-dimensional. That's not a typo. So this is an m by n matrix. M rows because each of the A's is m-dimensional, and n columns because there's n of them. These are m-dimensional. And X is n-dimensional, not m-dimensional. So these are important things to pay attention to. X has to be n-dimensional. The number of entries of X has to be the same as the number of columns of capital A, because those entries are going to be the weights in the linear combination, the coefficients. Then A times X is this linear combination. X1 plus A1 plus X2 plus A2 plus X3 plus A3, etc., dot, 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 through Xn times An. Did I say plus? X1 times A1 plus X2 times A2 plus dot, dot, dot times Xn times An. Note the non-boldface things and the boldface things. And the capital letter A, that's the matrix. Boldface X is a vector. These non-boldface little x's are numbers, scalars, times these boldface A's are vectors. And this is an RM. I didn't have to put this over here to define this thing. I'm just trying to emphasize that the answer is an m-dimensional vector. So we're taking an m by n matrix and multiplying times an n-dimensional vector, which is an n by 1 matrix. And the answer is m by 1. It turns out that to multiply these two numbers have to match. They're both n. And the answer has dimensions of the outer things, the m and the 1, m by 1. An m by 1 matrix, which is an m-dimensional vector. We can then define a linear transformation from Rn to Rm to be any such function with the property that there is a matrix like this that defines the transformation in this way. Say that again. What is a linear transformation from n-dimensional space to m-dimensional space? It's any function for which there is a matrix, capital A, that will be m by n. The numbers switch around their order, m by n, so that the formula for capital T can be written in the way you see here. T of x is a times x. And every time you see that, say it in your mind. T of x equals a times x. This is not a multiplication. This is a function, a vector being plugged into a function. This is a multiplication. This is a times x. This is analogous to, functions that you're used to. F of x equals a times x, where x and a are numbers. It's an analogous kind of thing. Isn't that beautiful? That is meant to be beautiful. That I can apply a linear function by effectively a simple multiplication, though it's a matrix times a vector. The operation preserving properties then follow from this. In particular, for example, the most general one, this one follows from this definition. It would be a good exercise for you to try to verify that this property is true, or maybe the more specialized properties if you don't feel like dealing with summation signs. I don't have time in this lecture. Maybe in a future lecture we'll look at verifying one of those, maybe in the next one. Okay? All right. Keep going here. We are going to get to visualizing like right now. Just like in lecture A, the visuals are very important for understanding the more symbolic. Same thing happens here. But to visualize things, we have to imagine things in lower dimensions because we're just not capable of imagining geometry in higher dimensions. We can still do math in higher dimensions, but it's hard to literally imagine them. All right, so we're going to build up our examples. We've talked about two-dimensional linear transformations from R2 to itself before in lecture 6b, and I'll remind you of that here at the end. But we could think about one-dimensional inputs and one-dimensional outputs. T goes from R to R. What's a linear transformation from R to R? It is this kind of thing. And no plus b's. If we want this to be a linear transformation, in the sense that we've defined it, we don't want to add non-zero constants. Of course, in calculus, you call things like this linear even if you did add a non-zero constant. The graph is a straight line. But for linear algebra, you do not want to allow constants there, because we want the operation preserving property to hold. That's the reason, because that generalizes to other things as well. So in this case, your b is going to be 0, and the graph, which is the way to visualize this, is going to go through the origin. Its vertical intercept will be 0. I've purposely written it a bunch of different ways. On purpose. This is a times x in the usual sense. That could be thought of as a 1-by-1 matrix. I could put parentheses around it. I could also put square brackets around it. So that's all I'm emphasizing there. That could be thought of as a matrix multiplication. This 1-by-1 matrix times that 1-by-1 matrix. I could call this 1-by-1 matrix capital A if I want. And I can think of it as a linear combination of the columns of A, where the entries of the vector x are the weights. Well, the columns of capital A is just one-dimensional column, A itself. There's your linear combination. X has got just one entry, x itself. X times A is a linear combination of the columns of capital A with the entries from the vector x as the weights. It's very simple in this case. It's helpful to realize these are all tied together. That's the point. We already know how to visualize this with an ordinary graph. Okay, so here I picked A to be 2. I can think of it as the number 2, or I can think of it as the 1 by 1 matrix 2. I can think of X as a number, I can think of it as a 1 by 1 matrix X. The graph is the usual kind of graph. Graph to the origin, slope of 2 in this case, vertical intercept of 0. You want to think of the horizontal axis as being the domain, which is R. That's the domain. And you're going to want to think of the vertical axis as being the codomain. We're going from R to itself. You don't want to think about the plane itself as being the domain or codomain. For this example, the next example, I think, the plane will be one of those two, the domain or codomain. But for this, you don't. A couple new terms that you should have heard of in the past. Well, first of all, the image of T, we introduced this notation last time. Also, you can think of that as T of R, is the sum of all outputs of this function is all of R. Why? Well, give me any number in the codomain, like 3.2. There's a number in the domain that gets mapped to it. 1.6. If this is 3.2 here, T of 1.6 equals 3.2. And I can do that for any number on the u-axis, for any number in the codomain, and therefore the image of this linear transformation is all of R. It's onto. Have you heard that word before? Onto. And that's going to be the case in general exactly when the A is non-zero as a number. And as a 1 by 1 matrix as well. Because if A is non-zero, A is going to be the slope of the graph. If it's non-zero, then every point on the u-axis will have an input that gets mapped to it. I'm using that word map, like I used in lecture 6b. It gets sent to it, or any possible output is an actual output. Another way to think about it, 3.2 is a possible output. It's an actual output because when you plug in 1.6, you actually do get 3.2. If A is 0, then it will not be onto, because the graph would be just the horizontal axis, and the image would just be the origin, 0 by itself. T is also 1-to-1. You remember what 1-to-1 means? It means it passes the horizontal line test. Every horizontal line goes through it no more than once. That doesn't happen with like x squared. Every possible output has exactly one input that gets mapped to it. Or at most one input, and actually exactly one in this case. Okay, these are going to be important words that we'll continue thinking about here in the other examples. Next example, one-dimensional inputs and two-dimensional outputs. T goes from R to R2. The input is one-dimensional. Think of it as a number. I can think of this as a 1 by 1 matrix or a one-dimensional vector. The output is two-dimensional. I'm writing as a 2 by 1 matrix or a two-dimensional vector here, AX and BX, and no constants being added. That could be thought of as X times the column vector of a matrix A. This would be the matrix A right here. And I could then think of that also as the matrix A times the vector X. A times the vector X, where this is now 2 by 1. This is 1 by 1. Those inner numbers match, so I can do the multiplication. The answer is going to be 2 by 1. The answer is a two-dimensional vector as well. Okay? It's confusing, I know. You just got to keep thinking about it. Keep listening carefully to what I say. How are these things visualized? They're typically visualized as what are called parametric curves, which is equivalent to a system of parametric equations. U equals AX and D equals BX in this case. The parameter is X. Usually with parametric equations, the parameter of choice is little t. And I could have done that here, but I wanted to be consistent with the other ones. So I'm calling the parameter x. A and b are fixed numbers. X is a variable. As x varies, both u and v vary. And you get a curve in the plane, which will happen to be a straight line. This best visualizes a motion on Mathematica. That's what I'm going to show you here in a second. Before I do that, note that this is there's never a situation where such a function would be onto. The output space is two-dimensional space in this case. There are going to be plenty of points in the plane that are not going to be on the line defined by these parametric equations. They're not going to be a possible output of this function, and therefore there's no way this is ever going to be onto. However, it's usually one-to-one. Though you could say more specifically it's going to be one-to-one if and only if A is not a 2x1 zero matrix. It's not 0, 0. That is, T is one-to-one if and only if either the little a or the little b is non-zero, or both are non-zero. All right, let's visualize this on Mathematica now. I'm not going to show you the details of the code here. No, let's not worry about it here. Okay, so the particular linear transformation from R to R2 that I'm talking about here has this formula. T of x is 3x, x. X really is just a real number here. The output is two-dimensional. Mathematica wouldn't let me format this nicer. 3x and x are u and v. U is 3x, v is x. That can be thought of as this 2x1 matrix times this 1x1 vector x. Capital A matrix is this matrix 3, 1. And if you let this play as x varies, you can think of it either as a set of points in red or as a bunch of arrows in blue, because there's that natural correspondence between points and their position vectors. And it is something that you're going to want to continue to think about. For any given point, anytime I stop this, the position vector for the given point, the point in this case being right here, it doesn't let me draw in Mathematica. Right there, the position vector goes from the origin to that point. It doesn't, you don't see it literally going that far, but that's what's meant to be the case. Okay, so it's going to be not onto for sure, because you're not, the codomain here is the entire plane, the entire UV plane. There are going to be plenty of points, any point not on that line that will not be a possible output, but it will be one-to-one. The only way such a function would not be one-to-one is if this were the zero matrix with two zeros there. And then the image would just be the origin in that case. Okay, back to the PowerPoint. On to the next example. We're almost getting close to being done here. Hang on. What about two-dimensional inputs and one-dimensional outputs? So I switch it around. Now from R2 to R instead of R to R2. Then you can think of the function in these various ways. T of x, and by the way, I could get the output name. I could call it u again. U would be a number in this case. They're thinking of it as being a number. This is T of xy equals this number, which I can think of as being a 1x1 matrix. And that could be thought of as a linear combination of two 1x1 matrices or vectors. And if I want to think of it as a matrix times the vector, there's the matrix A to use. This is capital A here. A 1x2 matrix. The columns of that matrix are one-dimensional, consisting of A for the first column and B for the second. The vector x has components x and y. Here's a linear combination of the columns of capital A with the entries of x and y as the weights. This is a 1x2 matrix times a 2x1 vector. You can multiply them because the inner numbers match. You get a 1x1 matrix or a number out. By the way, in the preceding slide, I don't know if I mentioned that A was 2x1 and X was 1x1. Or no, 1x2, excuse me. Did that happen? Oh, 1x1, and giving you a 2x1 vector in the end. That's what I want. How do you visualize a function like this, typically? It's going to be a surface. graph in three-dimensional space. Why is it in three-dimensional space if you don't see any R3 here? Well, it's just the typical way of visualizing it, like this. So the plane, the XY plane, X goes this direction, positive direction that way, Y goes into the screen, positive direction this way. The XY plane, draw out with some perspective here, not the best drawing, is your domain, that's R2, embedded in three-dimensional space, and the vertical axis, which I call Z here, is your codomain. There's your codomain, a one-dimensional codomain. The graph is a plane sitting inside three-dimensional space. For any given input, you get an output. It's because the domain is two-dimensional that you get a surface here, a two-dimensional thing. Such a function will never be one-to-one. Right? For any given number on the vertical axis here, say right there, there are going to be lots of points in the plane that get mapped to that. I dare not draw it here very well. I think maybe something about like that. That could be wrong. That would be the set of points, and you would have to go down to the plane here. It's some set of points down there that get mapped to that output. In fact, it would be a level curve, like we talked about in lecture 7a. We talked about this kind of thing in lecture 7a. Except now it's a linear function, so the graph is a plane rather than some nonlinear non-plane as we saw in lecture 7a. So it's never one-to-one. It's onto if and only if, capital A, this matrix is non-zero. This IFF is shorthand for if and only if. Capital A is non-zero. In other words, either little a or little b is non-zero, or both are non-zero. Coming back to our last example, I think this is the last slide. Yes, it's the last slide. R2 to R2. How did we visualize this? We talked about that in lecture 6b. And we talked about this already. You could visualize this as a mapping. It's less clear under what conditions T will be one-to-one and onto, though. Reflections in particular, though, are one-to-one and onto. And here is the reflection from the last lecture. Reflection across the horizontal axis. Capital A is not a matrix here, it's a set in this picture. So this capital A does not match that capital A. So capital A is this butterfly curve. T of A in blue is its image under the reflection across the horizontal axis. I'm labeling the axes differently. The input space is XY, the output space is UV, but they're both rectangular coordinate systems. Effectively, it is the same plane. I'm just labeling the axes differently. This particular function would be one-to-one and onto. For example, the point down here is going to be mapped to from the point up here, right about here or so, will be reflected down to that point across the horizontal axis. And that can happen for any point. Points on the horizontal axis itself get mapped to themselves. It also turns out to be one-to-one. For any given output, there's at most one input, and that should make some intuitive sense if you think about it. To end the lecture, let me just say that for this situation where you have a linear transformation where the domain and the codomain have the same dimension as a space, it's going to turn out that one-to-one and onto are actually equivalent to each other, which is not true in general for nonlinear functions. And it's also related to the determinant of this matrix. Maybe you've learned about determinants before. You may want to see if you can look that up and figure out how being one-to-one and or onto in this kind of situation is related to the determinant of that matrix. And that will be the end of this lecture. Thanks for watching.